Yes, we need rigorous termination criteria, and we can categorize them from the incredibly unsophisticated to the essential mathematical requirements. Let's quickly dismiss the crude approach first. The crude stop is simply specifying a fixed number of epochs. You just say run for 100 loops and then stop, which is easy. It's fast to implement, but it gives you zero guarantee of efficiency or quality. You might stop just before finding a much better minimum, or you might stop long after you started overfitting. It's an administrative stop, not an intelligence-driven one. So we move to the mathematically sound criteria, which focus on the state of the weight vector itself, the vector w. Right. We know that at a minimum of the error surface, let's call it ρ star, the error surface must be flat. Mathematically, this means the gradient vector, enabler E of w, must be 0. The gradient vector is a collection of all the partial derivatives of the error function with respect to every single weight. But how do we use that in practice if we can't exactly hit 0? We use the gradient-based criteria. We declare convergence when the magnitude of that gradient vector reaches a sufficiently small gradient threshold. The magnitude is measured using the Euclidean norm, which you can think of it as the overall length of the gradient vector. So if the vector is short, the slope is shallow. Exactly. If the Euclidean norm of the gradient vector is approaching 0, it means the system is barely learning anything new. It's a strong indicator that it has settled into a minimum. That makes perfect sense, that the learning naturally slows down as you approach flatness. What is the alternative, the one that focuses on the error value itself? That's the cost function-based criteria. This focuses on the idea that at a minimum, the cost function is stationary. It's not necessarily 0, but it's not changing much. Convergence is declared when the absolute rate of change in the average squared error per epoch is sufficiently small. Can you give us a sense of what sufficiently small means in a real system? Typically, this rate of change is considered small enough if it's consistently between, say, 0.1 and 0.01 change in the error measure per epoch. If you run 10 epochs and the error measure only dropped by 0.05 over that entire time, you've probably hit a plateau. You've likely hit stagnation, which is often a strong signal to stop. Now, let's tie this to the practical implementation that prevents us from overfitting, which is known as early stopping. This is essential in modern frameworks.